You probably think the internet lives in the cloud, beaming wirelessly through satellite, but 95% of all intercontinental data travels through literal cables on the ocean floor. Today I'm breaking down every hidden system that makes the internet instant, starting with the glass threads that make it all possible. Optical fiber cables. The entire global internet runs on strands of glass roughly the thickness of a human hair. A single mode fiber core is 8 to 10 micrometers wide, carrying light at 2/3 the speed of light in a vacuum. That means a signal crosses the 6,700 kilometers between New York and London in just 30 to 35 milliseconds. In 1988, the first transatlantic fiber cable, TAT8, carried 280 megabits per second. Today, cables like Maria haul 160 terabits per second. That is literally a million-fold increase, and experimental setups have already hit petabits. Over 400 active submarine cable systems span more than 1 million kilometers globally. These hair-thin glass cores sit thousands of meters underwater, engineered to survive 25 plus years of crushing pressure, with repeaters every 50 to 100 kilometers amplifying signals without any electrical conversion. Fragile glass that outlasts everything on the ocean floor, which is, not ideal for the fish. But if you think underwater cables are impressive, wait until you see the satellites trying to compete with them. Low-WOW's Earth orbit satellite. Everyone assumes fiber is the fastest way to send data across the planet, but it's not. Sometimes the fastest route is straight up into orbit. Before you dismiss this as insane, hear me out. Low Earth orbit satellites sit at 500 to 1,200 kilometers above the surface, close enough that a signal bounces up and back in 30 to 50 milliseconds total. Compare that to geostationary satellites at 35,186 kilometers that need 500 to 600 milliseconds just for the round trip. That's 10 times slower. But here's where it gets weird. For certain long-distance routes, LEO satellites with inter-satellite laser links can actually beat undersea fiber cables. The reason is stupidly simple. Light travels at 300,000 kilometers per second in vacuum, but only 200,000 kilometers per second in glass. If your data spends enough time in fiber, the slower speed adds up. Route that same packet through space instead, and the faster vacuum speed can more than make up for the extra distance of going up and down. Your data leaves the planet to arrive faster. Starlink alone has deployed over 5,000 operational satellites by the mid-2020s, with plans for tens of thousands total. Individual terminals pull 100 to 200 plus Mbps under good conditions. For rural areas with no fiber, this is transformative, but astronomers warn that thousands of bright satellites are wrecking optical and radio observations, and nobody's quite sure what happens when multiple constellations try to serve dense cities from overhead. At least LEO works now and scales globally. Unlike the horror show of trying to route everything through a handful of choke points on the ground, Internet Exchange Point. Here's a fun mystery. Why does traffic between two ISPs in the same city sometimes fly to another continent before coming back? The answer is internet exchange points, and without them, the internet would be an expensive, slow nightmare. An IXP is basically a big shared switch sitting in a data center where hundreds or thousands of networks plug in and exchange traffic directly. Think of it as a highway interchange for packets. The largest ones like Diakis in Frankfurt, AMS Nijm in Amsterdam, and Lynx in London handle over 10 terabits per second at peak. That's more data than most countries generate in total. Here's where it gets weird. Without a local IXP, two ISPs in the same country might route your packets through a third party on another continent, adding thousands of kilometers and tens of milliseconds of delay. With peering at an IXP, those same packets cross a single switch in a fraction of a millisecond. The difference between a snappy website and a sluggish one often comes down to whether your ISP bothers to peer locally. IXPs operate as non-profit cooperatives or for-profit entities, and there's ongoing tension between open multilateral peering, where everyone exchanges traffic freely, and selective peering, where big networks charge smaller ones for access. A single room full of switches can shave tens of milliseconds off every connection for millions of users, but if you think routing through IXPs is complicated, wait until you hear about the protocol that actually decides which path your packets take. The entire internet runs on an honor system. Border Gateway Protocol, BGP, is the protocol that stitches the internet's thousands of independent networks together, and it was first specified in 1989. Routers establish sessions over TCP port 179 and fire update messages at each other, exchanging routes with attributes like ASPath that prevent infinite loops and let operators enforce policy. Sounds legit. Here's the thing. The original BGP had zero cryptographic authentication. It just trusted that everyone was telling the truth about which addresses they owned. And that is, not ideal. One typo from a single operator can accidentally hijack massive address blocks worldwide. In 2008, a Pakistani ISP tried to block YouTube locally by announcing a more specific route. That announcement propagated globally, and YouTube vanished from the entire planet for hours. One config mistake. Global blackout. Efforts like RPKI and BGPsec exist to add cryptographic validation, but deployment is glacial. BGP is a necessary evil that somehow survives despite itself. But if you think routing all traffic to one location sounds risky, wait until you see what happens when we give that exact same address to hundreds of machines at once. You type 8.8.8.8 and you think you're hitting one specific Google server somewhere in California. You're not. You're being lied to beautifully. Anycast routing. Anycast is a networking sleight of hand where hundreds of physical machines scattered across the planet all answer to the exact same IP address. Your device has zero idea this is happening. It just sends a packet to that address like normal. But BGP, the protocol we just covered, intercepts that packet and steers it to whichever instance is closest according to routing policy. So someone in Tokyo hitting 1.1.1.1 talks to a Cloudflare server in Tokyo. Someone in London hits the same address and lands on a machine in London. Same numbers, different continents, different physical hardware. The magic is completely invisible, and it is fast. Users near a point of presence routinely see round-trip times under 10 milliseconds. DNS root servers rely on this exact trick, with single logical root identities replicated across dozens of global cities. But here's where it gets useful. If an entire data center catches fire or drops offline, its BGP announcement simply vanishes. Traffic automatically reroutes to the next best site. Zero client reconfiguration, zero downtime. The internet just heals around the hole, which is, not ideal for the data center, but great for everyone else. But if you think routing is clever, wait until you see the system that actually tells those packets where to go in the first place. Everyone thinks DNS is just the internet's phone book, but it's not. It's a constantly updated policy-driven steering system that decides where your traffic actually goes, and today I'm breaking down exactly how this invisible director works. Starting with the guy who built it, domain name system, Paul Macapetris created DNS in 1983, replacing static host files with a hierarchical, delegated naming architecture. Queries typically fire over UDP port 53, bouncing from root servers through TLD servers down to authoritative name servers. But here's the thing, DNS isn't some dusty directory. Large websites use it to dynamically steer users to different IP addresses based on geography, load balancing, or A/B testing. Hey, you're in Berlin, go to this server. You're in Tokyo, go to that one. The real magic is caching. Your first query might add tens of milliseconds, traversing the entire hierarchy, but once that answer is cached, subsequent lookups return in microseconds to a few milliseconds. This is why time to live values matter. Common TTLs range from 300 seconds to 86,400 seconds. That 24-hour maximum is exactly why DNS changes don't propagate instantly everywhere. Your resolver holds onto the old address until the timer expires. Then there's the encryption war. DNS over HTTPS and DNS over TLS encrypt your queries, stopping ISPs from snooping. But this sparks a real debate. Privacy gains versus centralization risks and network management complications. It's a power struggle, shifting control from ISPs to application providers, but turning names into addresses is only step one. Next, we need to understand the protocol that actually moves the data across the planet. Transmission Control Protocol and Internet Protocol. Every time you load a web page, watch a video, or send a message, you're relying on two protocols that make a chaotic, unreliable reliable network feel like a direct wire between you and the server, TCP and IP. And they're doing an absurd amount of invisible work every single second to maintain that illusion. Here's the thing, the internet is not a stable connection. It's thousands of routers and cables that packets bounce through, and any one of them can drop your data, delay it, or send it on a completely wrong path. IP handles the addressing and routing, getting packets from point A to point B on a best effort basis, which is a polite way of saying we'll try but no promises. IPv4 uses 32-bit addresses for roughly 4.3 billion unique addresses. IPv6 expands that to 128 bits, enough to assign an address to every grain of sand on Earth, and still have room left over. But IP alone is not enough. It doesn't care if your packets arrive out of order, get duplicated, or vanish entirely. That's where TCP comes in. TCP builds a rock-solid ordered byte stream on top of IP's unreliable delivery. It divides your data in segments, assigns sequence numbers, sends acknowledgements, and retransmits anything that gets lost. It uses sliding windows and congestion control to manage bandwidth without overwhelming the network. All of this happens in your operating system's kernel transparently while you browse. And here's the part nobody thinks about. When your page loads slowly, it's often not your bandwidth. It's TCP. Congestion control, retransmissions, and connection overhead dominate load times. People blame their ISP's speed, but the real bottleneck is frequently the protocol behavior itself. But if you think reliable connections are the only layer holding the web together, wait until you see what happens when those connections need to be encrypted. Hypertext Transfer Protocol Secure. Almost every website you visit now has a little padlock icon in the address bar, and that means HTTPS is doing its thing. But here's the kicker. When this was first introduced in the mid-1990s with Netscape's SSL, people assumed encrypting everything would make the internet crawl. Turns out, NOMTPS combines regular HTTP with transport layer security to give you confidentiality, integrity, and server authentication. By the late 2010s, over 80% of page loads in many regions were encrypted, and Let's Encrypt alone had issued hundreds of millions of free certificates. Modern TLS 1.3 can complete in one round trip under optimal conditions, adding well under 100 milliseconds to your first request. A transatlantic round trip is 60 to 80 milliseconds, so the entire process of negotiating keys and setting up an encrypted channel is basically a rounding error. Hardware acceleration lets servers terminate millions of HTTPS connections per second without breaking a sweat. But here's where people get confused. That padlock icon does not mean the site is safe, reputable, or even legitimate. It only means the connection between you and the server is encrypted. A phishing site can have perfect HTTPS and still steal your credit card. The whole system depends on certificate authorities being honest and competent, and incidents where CAs were compromised or misissued certificates have happened more than once. There's also the ongoing tension between the uncrypt everything movement and the reality that HTTPS makes network inspection harder for enterprises, parents, and law enforcement. At least with HTTPS, your data isn't flying across the internet plain text, unlike the massive distributed caching systems that make sure it doesn't have to fly very far at all. Content delivery networks. When you stream a show or load a website, you probably assume that data comes from some distant server farm. Turns out, no. The bytes are already sitting in your city or literally inside your internet provider's network waiting for you. That's what content delivery networks do. The modern CDN industry kicked off in 1998 when Akamai was founded. Now, major players like Akamai, Cloudflare, Fastly, plus DIY systems from Netflix and Google operate thousands of edge servers worldwide. A typical CDN node is racks of commodity hardware with tens to hundreds of terabytes of SSD storage. For popular platforms, a massive fraction of bytes originate from CDN caches within your country, or ISP, rather than crossing an ocean. This proximity drops round-trip times from hundreds of milliseconds to single digits, which is the difference between smooth 4K and constant buffer. CDNs pre-position content during off-peak hours, so the heavy stuff is already there when everyone clicks at once. During major live events, CDNs serve tens of terabits per second globally without breaking a sweat. The misconception is that the website is one distant server. The reality is distributed caching layers that follow you geographically. But here's the dark side: concentration. A huge portion of web traffic funnels through a small number of CDN, creating single points of failure. A misconfiguration or outage at a major CDN has rendered large swaths of the web unreachable for hours. When one breaks, huge chunks of the internet just vanish. At least CDNs are stateless cache. Load balancers, on the other hand, actively decide which backend server handles your request in real time, and if they fail, things get messy fast. Load balancer. You type in api.example.com and your request gets handled. Simple. But that single address is a lie. Behind it could be 2 machines or 200, and something has to decide which one gets your traffic. That something is the load balance. Operating at layer 4 or layer 7, load balancers make routing decisions based on IP addresses, ports, URLs, or even application data. They monitor active connections, response times, error rates, and constantly ping backend servers with health check. If an instance starts lagging or fails entirely, the load balancer just stops sending it traffic. No drama, no outage, it simply routes around the problem, using algorithms like least connections or weighted round robin, ensuring no single machine becomes a bottleneck. When AWS launched Elastic Load Balancing in 2009, it democratized horizontally scalable architectures for everyone. Small teams could suddenly spin up dozens of instances behind one endpoint, and the load balancer would invisibly spread the load. Combine that with auto scaling, and traffic surges that would have cratered a site instead get smoothed out. Your successive requests might hit completely different machines and completely different availability zones, and you would never notice. But here's where it gets complicated. Sticky sessions let you pin a user to one backend to preserve their state. Great for simplicity, terrible for even distribution. Go fully stateless instead, and you gain perfect scalability, but shove all that state into shared databases. Engineers still argue about this trade-off today, and if your site feels slow, everyone blames the servers. Turns out, no. A saturated load balancer is often the real bottleneck, choking traffic while the backends sit there practically idle. But even the smartest load balancer can't fix what happens when the data itself lives too far away, which is exactly why the next layer has to get physical. Everyone thinks slapping more RAM or a faster CPU at a server fixes slow load times. Turns out, no. Storage latency is almost always the real bottleneck, and the solution is solid-state drive caching. Solid-state drive caching, NVMe SSDs connected over PCIe deliver random read latencies in the tens to hundreds of microseconds, pushing hundreds of thousands of input, JICE output operations per second. Hard disk drives, they sit around millisecond latencies and barely scratch a few hundred IOPS. When a data center stores popular content or database results on an SSD, that request is satisfied in roughly 100 microseconds. Grab that exact same data from a hard drive and you are looking at 10 milliseconds. Fetch it from remote storage and you are staring down hundreds of milliseconds. Psychological studies show delays below 100 milliseconds feel instantaneous to humans. An SSD cache hit operates 3 orders of magnitude below that threshold. You genuinely cannot perceive it, it just registers as already there. But here's where it gets complicated. Flash memory has finite write endurance. Engineers must balance cache hit rates against write amplification. Otherwise, they prematurely wear out the drives, which is, not ideal. They often combine SSDs with larger HDD pools to create cost-effective tiers, coordinating caches across distributed systems without creating coherence nightmares. It's a hidden balancing act, keeping everything feeling instant. But compressing storage time means nothing if the computer itself is still sitting thousands of kilometers away, which is why everything is now moving to the edge. It's edge computing. Here's the thing about the speed of light. You can't cheat it. If your server is 5,000 kilometers away and you need a response, you're paying at least 50 milliseconds round trip no matter how fast your connection is. Physics doesn't negotiate, but edge computing found a loophole. Instead of trying to send signals faster, it just moves the server closer to you. The idea is simple. Rather than centralizing all computation in a few massive cloud data centers, you distribute smaller nodes everywhere, at cell towers, in metro areas, at the ISP level, sometimes even on your street. When you interact with a service, you're not talking to a machine in Virginia. You're talking to one 10 kilometers away. Suddenly, that 50 millisecond delay drops to 5. For cloud gaming, AR, or industrial control systems that need sub 20 millisecond response times, it's the difference between possible and physically impossible. Cloudflare Workers launched in 2007 as one of the first big serverless edge platforms. AWS followed with Lambda Edge. Telecom companies started building edge computing into 5G base stations, promising cloud-scale computation with LAN-level latency. Edge nodes also handle things smarter. A factory floor with 1,000 sensors spewing gigabytes of data every hour doesn't need to send all that to the cloud. An edge server filters and aggregates locally, summarizing the readings into a few megabytes of actionable insight. The central cloud gets what it needs, local systems respond instantly, and nobody's paying to ship raw noise across the internet. But here's where it gets complicated. Managing thousands of distributed edge locations is not the same as running 3 big data centers. Every site needs power, cooling, security, and someone to fix it when hardware dies. You're trading centralized simplicity for distributed chaos. A lot of things people imagine requiring edge computing work fine with a well-placed CDN cache. The gap between 5G powered edge hype and the reality of managing that many locations is still pretty wide. The ultimate idea is that the computer should happen where the data is. Edge computing is the final piece of making the internet feel instant, because for stuff that really can't tolerate delay, it eliminates the delay at the source. If you enjoyed this video and want to see more, click the video on the screen now.